Hello, my name is James Neville and I'm here to talk about a technology called Mesh Adaptation, available in Autodesk Simulation CFD 2013. The basic workflow for setting up a mesh in Simulation CFD 2013 will be familiar to existing users. The ability to suppress parts from the meshing process, robust geometry-based mesh auto-sizing, the ability to adjust sizes for edges, surfaces, and volumes, and user-definable refinement regions for additional control over mesh density remain largely unchanged. An additional option is now available which allows for results-based mesh refinement or mesh adaptation. Mesh adaptation queries the existing results from a completed simulation to determine where additional mesh is required. Several additional simulations are conducted in a cyclical process to achieve the final adapted solution. Mesh adaptation, paired with existing geometry-based auto-sizing technology in Simulation CFD 2013, provides a complete meshing solution. Mesh adaptation strives to provide mesh independence. This technology helps to achieve the ideal mesh distribution for each individual scenario. With increased mesh quality comes greater results accuracy and resolution. While it may be clear where additional mesh is needed for some areas, like the heat plume above a natural convection model, or the wake region behind an external aerodynamics model, other regions may not be so obvious. Mesh adaptation refines all regions as needed. One approach to meshing is to over-refine large portions of a model in hopes to capture the final flow and thermal fields. This method will probably provide decent simulation results, but many elements may be wasted where they are not necessary, causing model size and simulation time to increase. Adaptation helps to conserve resources by refining the mesh where needed and coarsening the mesh when possible. While mesh refinement regions are still available for advanced users or users who want the ultimate level of control over the simulation model, the meshing process can be simplified down to two steps: auto-sizing and enabling adaptation. The validity of a CFD solution is based in large part upon the quality of the mesh. Users can rest assured that their solution is of greater quality with less setup input. These benefits combine to enable users to get more value out of Simulation CFD 2013. Next, I'll go through a quick example to show how to enable and control mesh adaptation, and I'll showcase some adapted results. This model here is a two-element rear wing assembly for a motorsports application. The setup for this simulation is fairly straightforward and similar to any external aerodynamics analysis. I'm using a half-symmetry version here, and I've created a virtual wind tunnel around my rear wing assembly. The assembly itself is suppressed, and I've elected to use the default auto size. When the simulation is ready to run, there is now an additional Adaptation tab to be found in the Solve dialog. By default, enabling adaptation will result in 3 additional simulation cycles to be performed after the first simulation is complete. Each cycle will be more refined than the last. There are 2 main options when using adaptation. Checking the box for save cycles will clone each cycle after it is completed. This is useful for a mesh-independent study and to be able to compare results for each cycle. Without save cycles, the only solution available when adaptation completes is the final solution. The other main option is to allow coarsening. This self-explanatory checkbox allows the mesh to coarsen when possible, helping to reduce the overall mesh size. While the default adaptation settings are designed to work for most applications, additional options can be enabled to suit certain scenarios. Advanced parameters dictate how quickly and uniformly the mesh will adapt and are similar to parameters already found in the advanced meshing dialog. Let's jump into some results. The first set of images compares the adapted solution on the left to the original solution on the right. It's clear that additional mesh density has been added to the adapted solution, concentrated in areas where velocity and pressure gradients are highest. The high pressure region at the leading edge of the wing profile, the high velocity zone under the wing's main element, and the slot gap between the two elements where flow accelerates are great examples of where adaptation will have the greatest impact. Here is a close-up view of the slot gap velocity between the two elements. Note the smooth contours of the adapted solution on the left. A results plane placed at the bottom of the wing end plate reveals a large flow disturbance downstream of the wing assembly. This is a great example of a region which requires additional mesh density that might not be expected prior to the first simulation. A similar results plane placed at the top of the wing end plate reveals another flow disturbance created near the outboard region of the assembly. Again, mesh adaptation picks up on this flow phenomena and refines accordingly. An isovelocity surface helps to visualize the two flow disturbances. The low pressure under the wing causes a pressure differential between the free stream air outside the end plate and the air passing under the wing. Air outside the end plate rushes under the end plate as it passes the wing assembly, developing into a large downstream vortex. A similar effect is seen at the top of the end plate, where high pressure air escapes over the edge of the assembly. These two vortices are captured perfectly with mesh adaptation. Particle traces released into the vortices show how the two disturbances are generated. Comparing the adapted solution to the initial solution, the particle paths are considerably smoother and the vortex spirals are captured more realistically.